your hardware, your software, and your bandwidth allows it, please keep your cameras on at all times. Present whenever you're ready, and then we'll proceed with the interview.
Teacher, just one quick question before we start.
Yes.
My Wi-Fi is very bad, so if I'm like kind of glitchy, it's because of that. I'm trying to use my cellular data.
Don't do that. If you think
No worries. It won't affect me unless it's like an hour-long presentation, but I don't think so.
Well, that's what I meant with your software, hardware, and bandwidth. But
it's all right. It's all right.
Okay, thank you. So go ahead whenever you're ready.
Can I share?
Please.
Can you see it?
Yeah.
Okay. Right.
Okay. So we're gonna start. I'm looking at like this. We're gonna start, and this is we're team 2, and my team is composed by Natalia Franco, Mateo Rafael Ruiz Perez, Andrea Carolina Gonzalez, and me, Fabricio Neira. Okay, so then next slide, Mateo. Okay, so the introduction, and these are some of the concepts we needed to be very familiarized with during and before the start of this challenge and the problematics we were trying to solve, which are the magnetic field. And this consists basically of the field of influence produced by a magnet or electrical current, which as we see is produced when current is flowing through a wire or something like that. It produces a magnetic field, right? Electromagnetism and the interaction among all electrically charged objects with magnetic moments and the electromagnetic field, as well as electromagnetic induction, which is created by way of movement of a magnetic field around an electric conductor. And if you can go to the next slide, Mateo, please, because there are some few other concepts that we need to, these ones. And well, these are also some of the concepts we used during the solving of the challenge, which are the linear motor, which was basically the thing we built and will proceed to simulate in MATLAB and all of that. You'll see that in a minute, which works similarly to a rotary servo motors operating with an alternating current power supply and a servo controller. Over here, let me see if I can point this out real quick. Over here, we have the linear motor example, right? Anyway, and the magnetic flux, which is the path of this magnetic reluctance is the one the magnetic field follows. The magnetic field is made of either one or multiple closed loops paths containing the magnetic flux, something like we have over here. And Faraday's law is something we use, even though it was one of the latest things we saw. It was something that was crucial for the solving of the challenge, which states that the rate of change of the magnetic flux that goes across the circuits is proportional to the magnitude of the electromagnetic of the EMF, which is the electromagnetic field induced. And next, please, Mateo. Mateo, your microphone is off.
Oh, sorry. For the considerations for the solution of this challenge, we at first start working with an ideal model with a constant magnetic field. So we apply some differential equations, such as distance, the differential of distance over time and the differential of velocity over time. And we model the kinematics of the road within the linear motor. Nevertheless, when we start talking about the solution of the challenge, we know that the linear motor have a non-constant magnetic field. So we build an Excel sheet to observe the behavior of the road with a non-constant magnetic field. And after this, we modulate a MATLAB code so we can apply the formulas and see how it moves along the road.
And for the prototype design and operation, for the constructed linear motor prototype, we use the south pole of the magnets and we glue them to the piece of wood. And we also made the design in SolidWorks to make to have a more precise prototype. And also the actual applications for the linear motor are used to actuate belt conveyors, shuttles in textile looms, and other devices requiring a linear motion. And also the values of the components. For the current, we used 0.9 amperes. The voltage was 9 volts. The distance between the cables were 5 centimeters, and the mass was 2 grams of the rod. And also the length of the rails was 25.6 centimeters, and the number of magnets that we used were 8. And now we are going to watch the prototype operation video. Here we show that if we change the current, the rod will go to the other direction of the linear motor.
So for the analytical modeling, we use at first Newton's second law, that is the force is equal to the mass to the acceleration, and the mass is equal to the differential of velocity over time, where, well, force is applied to the mass and mass is of the metal bar, we have to accelerate. Then the mathematical models we use is the force of the magnetic field, that is the longitude of the cable, the distance between the cables, the current, and the magnetic field, the power, that is the force times the velocity, work, that is force over times time, and the acceleration, that is the force over the mass. Then we use energy, that is mass times velocity squared over 2. The final velocity that we have 2 times the acceleration times the change in x, so the distance, plus the first velocity, the initial velocity squared. And at the final, we have time, the change in time, that is final velocity minus initial velocity over acceleration.
And well, first of all, we made a simulation of how may look the magnetic field. Here we use only 3 values of our magnetic field, considering the center, and then a centimeter apart, and then another centimeter, to build up 1 magnet, and then we apply this code for the 8 magnets we had. Next one, please. And well, sorry.
So for the acceleration stage, we first measure the magnetic field, that is referred as VMT, that is microteslas. Then we have the magnetic field that we have to model it on Tesla, so we divide it over 1,000. Then we have the distance, the force that we show in the mathematical formulas, the acceleration, the velocity, the kinetic energy, and the time. For the distance, we did a while loop that says that the x, what is less than the last x, the max x, we are gonna end on a step. So it will be iterating over the, well, yeah, the steps. The velocity, we create a serials value of length of the distance, and it was evaluating the length of x minus 1, so we can add the velocity 1 with the formula that we showed before. And for the time, we did do a for, and we iterated with the same x values and the same formula that we show you, that is time plus final velocity minus initial velocity over acceleration. So this is for the acceleration stage. We did the simulation in MATLAB. So as we can see with the, with the magnetic field, that is non-constant. So we can see here that it's fluctuating. We can see this as the magnets. Oh, sorry. We can see this as the magnets. That they're going up and down. This is the magnetic field over the position. Then we did the simulation for all the variables we needed, all the graphs. We have the acceleration versus the time that is accelerating, and it's, well, fluctuating too over the magnets, magnetic field. Then we have the position over time. This is the velocity. You can see that it's exponential. And the velocity versus time, that is acceleration, that we can see that it's a constant upgoing linear equation. We have the acceleration, the force versus time. We can see that it's really the same as the one in acceleration versus time. We just change the values, that is the force. And the energy over time, that is really like the position versus time, just with energy over time.
And well, once we had the accelerating stage, we passed to the braking stage, where now is the same formulas. Nevertheless, we had two conditions now, which is the free distance, the distance without any magnets, where there is no acceleration, there is no force, and things like that. But as it is an ideal model, the rod will continue moving because we're not considering friction or anything like that. So for a certain distance, that in our case, we consider a distance of what it will be 5 magnets, but it's a distance without the magnets, where it will be a constant velocity, which will be reflected in a position that will start to passivize, to say in some way, with no force, no acceleration, and well, the energy is with the same formula we used last time. And when the free distance is over, we now start with the braking stage, which we consider just one magnet, a very powerful magnet, which will cause to stop in just one of these steps. And in here, well, we have another acceleration that is a bigger acceleration and negative acceleration, because it's braking, it's slowing down the rod. We also have a force, a negative force, and we all calculated all these values based basically on the kinetic energy, which the rod ended the accelerating stage, because it's the energy we need to stop at the end. Next, please. Well, in here we can see how at first the magnetic field is in 0, because it's the distance that we have no magnets, and then it suddenly drops to a negative value, because as we mentioned, we use the south poles of the magnets. So to the braking stage, we need to use in this case a north pole magnet. So we need to change the sign to make this difference. That is because we have a negative magnetic field. Next, please. And well, just like in acceleration, we modeled all the concepts based on time. And in all of them, we can see first the free distance without magnets. In acceleration is a line in 0. In position versus time is the time that starts, is the position, sorry, that starts to getting to a maximum value, the velocity is constant, and the force is 0, and the energy is also constant, while this free distance. And once the distance is finished, we can see that acceleration drops to a negative value, as I mentioned. The position stays in a constant value due to the fact that we have no longer velocity, so the rod is not moving anymore. And the velocity reached 0, and the force is a negative value, also derived for the acceleration. And the kinetic energy also arrives to 0. Sorry, I missed that.
So for the complete simulation, we can see here that these are the two parts at it. Well, the three parts actually. This is when it's accelerating through the linear motor. This is when there's no magnets along the cardboard piece, and then we can see the drop. We have here the same graph we did all over time. You can see the acceleration, how it is fluctuating, then it goes as constant, as 0, and then it drops. And it stays in 0 when it stops. The position versus the time. The position is going up, up. We have like it's moving the rod, and then it goes and stops. Then we have the velocity that is increasing. Because of the acceleration, then it stops. There is no acceleration, and then the acceleration is negative, tends to 0. Then we have the force, same as the acceleration versus time. The magnetic field is fluctuating, so the force is fluctuating. Then it comes to a constant value, then it drops to 0 and stays there. And for the end, we have the energy that is really similar to the velocity versus time. That the energy tells us that we are generating or experimenting an energy, then that it is constant, and then it drops at the same as the acceleration drops. So yes, this is a complete simulation, and this is all the gas over time.
And for the solution, we successfully built a direct current linear motor prototype based on a sliding bar that moves along a rail with permanent magnets, and it include an external magnetic brake that creates a braking effect due to current flowing through the rod.
Okay, so for the conclusions, well, we also the variables that we could change. The ones were the length, the free distance, the number of magnets, and all of those. And so we, after doing some trials, we changed the variables, playing around with them. We realized that the graphs did not actually change significantly. What did change were the values of the graphs, but they kind of resembled the graphs we now presented to you guys. So that's something that was really outstanding for us, something really interesting. And yeah, as Natalia also said, or I think it was Mateo as well. And well, we worked with both ideal and unideal formulas and models. And in this challenge in particular, we use more of the latter, which are the non-ideal formulas, because well, we have a non-constant magnetic field and stuff like that. So we have to, it was a bit more complex, but at the end we managed to push through. And well, yeah, I think that's all of that. Yeah.
Thank you. That will be
Well,
all.
thank you, everybody.
Thank you.
Okay, so let me start with the questions. So Andrea, you show us the actual working of your motor, and after that, some of you show us the actual values that, well, I believe you mentioned the actual values, the current, the voltage, and all that. What will be the values that you will change, or what would you improve for your motor to work, maybe for the bar to go faster, of the values that you presented? After you build it, you use it, so like, I may have changed this to make it better. what will you have choose and why?
Well, to make it faster, I will use a bigger voltage. So for the linear motor prototype that we use a 9 volts battery. So I will increase the voltage to make the rod faster.
So why the voltage? Like how the voltage increases the velocity?
Well, we try to we made that question when we were doing the simulation, and if we go to the power equation, we can see that it's the velocity, but well, we for the voltage,
If you
it
have more
wouldn't-
voltage, what will increase?
the velocity of the rod.
Yeah, but that's like the end result. Why the voltage is how the bar knows that you have a 9-volt battery or a 12-volt battery or a 24-volt battery. What happens to the bar, the actual moving bar, if you just change the battery?
Well,
For a different voltage.
It must be a
Uh,
chain. It must be a chain of effect, right? Like Paco says, the end result is incrementing the velocity, but changing voltage is going to change what, and this is going to
Okay.
change what until we get higher speed.
Well, if we change the voltage, it will change also the current of the linear motor, and then it will change all the variables of the mathematical models that we have, the force, the power, the work, because all of these equations have the current.
Will the magnetic field be affected?
The magnetic field, yeah.
How?
And if we have the equation of the force, that it's equal to the length of the wire, the current, and the magnetic field, then it is, I don't know, inversely proportional to the current. So if
Okay.
if we I don't know, if we decrease the current, the magnetic field will increase, and vice versa.
Okay, so who produces the magnetic field?
The force, the length of the wire, and the current.
And what about the magnetic force? What is
Well,
the difference between magnetic field and magnetic force?
The magnetic field and the magnetic force, it's the direction of the magnetic force is going to be the direction of the magnetic. No, I'm sorry.
Do you remember your right-hand rule that you have your force and your magnetic field always perpendicular?
Mhm.
So what is the difference between magnetic field and magnetic force?
The magnetic force.
Can I move to the formulas in the presentation?
Sure, just move around. Can you point which one of, well, okay, go ahead.
Hmm?
Go ahead.
Well, sorry, the magnetic force is the one that is going to like to give the rod the direction where it has to go.
Okay.
So if we have the magnetic field going, because it's going this way, like the north and the south pole, because we have the south pole of the magnets, then the force is going to be like this way, because it is going like that. And we have the current.
So final answer, what is the difference between magnetic force and magnetic field? Because you're just like going in cycles. The difference between magnetic force and magnetic field. Which one in those equations, which letter is magnetic force and which letter is magnetic field?
The F is the magnetic force, is,
Okay.
and the B is the magnetic field.
And are they pointing in the same direction?
No,
No. So who produces the magnetic field?
the magnet.
Okay. So if you change your battery, will the magnet change?
No,
So the force will change because you're changing what if you change the voltage? L, I, or B?
it will be changing the current.
Only the current, right?
Mhm.
Okay. Thank you very much, Andrea. Let me see. Yes, Fabricio, you mentioned something about the last thing you learned, which was induction. I believe it was a little before the actual plots. Can you explain what is induction or induced current?
Yeah.
Induced voltage?
Wait.
You said something about the last thing we learned about induction and something else. What is
Oh.
induction?
Yeah, okay. Okay, so when we have a variable magnetic field, it's the, how can I say? Okay, if I'm not mistaken, for example, this works, can you go to the presentation where the part where it says something about the motors, Mateo? I think it's a bit before that. Before. Okay.
Right there.
Yeah, so this, as we saw in class, this is how basically most motors works nowadays. So this is a basic principle, right? We have the magnets, and when current starts flowing through them, it creates a magnetic field around the wire, or around the wire, let's call it. And that's gonna start causing it to spin. So it's gonna create a force. The force created by this its own magnetic field, as we can see over here. Let me see if I can, this force. And the current is going like this, right? It's going here and here. And we already have this magnetic field going from north to south. So when applied to the current, it's going to start creating the movement of the motor. So that's what it states is the electromotive force produced by a magnetic field. If I'm not mistaken, once again, this is how most motors works nowadays, or this is the basic principle that most motors use. For example, I overheard this is basically how one of those, how can I say, fans, un ventilador de piso, that's how they work, yeah, right. Yeah, it was in the video, so that we can show us.
Around that, yes.
Yeah, around that. Yeah, I'm no expert. But yeah, that's if I'm mistaken, that's what it basically is, right? But yeah, I don't know if you want me to go a bit deeper into it or not.
No, I think that's good enough, Fabricio. Thank you. Well, yeah, the electric motors, like fans or something like that,
Yeah.
work with that principle. But okay, let's move a little forward because we're on time. Luis, do you want to ask something, or Natalia and Mateo haven't had
Yeah.
questions yet?
Sure, yeah. Can you guys go to the slide where you have the magnetic field versus position, please? That one.
The
That one.
acceleration part or the braking or the completion?
No, that one is fine. The magnetic field coming from the magnets. Why do we have all these jagged lines and very erratic magnetic field? Because I was expecting maybe something kind of a repeating pattern, because we have a repeating similar magnets, Mateo.
Yeah, well, we modeled this equation, well, this simulation, sorry, we did an experiment in the last class of the challenge, where we have a sensor going through the magnetic field, and we get this in micro Teslas, then we change it to Tesla. So we did this in Arduino, and we could see that it's fluctuating, but it would not, the sensor that was like receiving the value of the magnetic field was not receiving like really constant values. So well, yeah, this is really like, this is how we see that it's fluctuating, that it's going across the magnets, the magnetic field. So we can see that it goes up when it's at maximum point of the magnet. It is here. That is where it's going out, and then goes down when it's go through the space with no magnets, and then we go to the next magnet. So these peaks, we can say that are the magnets, the 8 magnets we have.
Yeah, so what would you say the reason is for not having like a very periodic kind of peaks?
You mean to have more?
I mean, if the
constant?
if the magnets were similar, were kind of equal, I would expect to have the same peak for one magnet, the same peak for the next magnet, and so on. So it's some kind of repeating pattern, and that's not really what we're looking at. So why is that?
Yeah, as I said, this happened because of the practical like sensor when we measure the actual magnetic field. Maybe
it's the sensor. So you blame the sensor completely.
Yes.
If you were to do this sensing a little more in detail, you would get more more of the repeating pattern.
Well, I think if we did it like with less time, because first we model it with the step of time, then we transform it to position. So if we do it like more, how you say, like less faster, like slower, we can see like the constant magnetic field. Like the sensor will catch the magnetic field at each point, constant.
All right. Okay. Now, can you go to the break stage plot? Maybe that one, maybe the one with the, maybe one before, the slide before, that one. Yeah, that one. So this plot is telling me that that I will need a magnet of some kind that has magnetic field of around 0.6 Tesla, right? In practice, do you think this scheme is feasible? Having this braking scheme in practice, If we were to ask you to build the braking stage,
You want me to answer?
what would be the difficulties? Yes, Mateo.
Well, we can see here it goes to 0 and then you have a really big drop. So we are using actually a 10 a magnet 10 times bigger than the other magnets, the one in the accelerating path. So I don't think this will be like really useful. Imagine we have a like a train. Well, it will come to a drop like really fast, so it will be no good for the stop. So maybe we could use like we saw the solenoid, and it will go like we will have a, or we can use like more magnets, like this 10 times bigger magnet divided into 3 maybe, and it will come to in decreasing, like, you know, 3 Teslas, look, 0.2 Teslas, 0.4 Teslas, and then a magnet of 0.6 Teslas. So it will be not that, it will be like not
Okay.
constant.
So yes, if this, okay, if this was a train of some kind and you wouldn't want it to break that fast, like you said, but also, what was the magnitude of the magnetic field of your magnets? Remember the order of magnitude? I think I saw some numbers like 40 or 50 milliteslas, maybe?
Yes, it's
All right. Okay.
0.0.
Yeah, like like 80 milli. Yeah.
Okay, something
Yes.
like 80 milliteslas. So compare this number with this number.
With the one in the bottom?
Yes, the one that you're supposed to require for the breaking stage.
It's 10 times bigger, approx.
It's not 10 times. It's not 10 times.
Well, if we convert this millitesla to Tesla, we'll have 0.4. No, 0.04. So it will be, if we multiply that by 10, we will have.
Oh, okay.
Tesla.
Yeah. Sorry. Yeah. Sorry. Yes. Okay. So, when you bought your magnets and all of that, building your motor, do you think it would be easy to find magnets with this magnetic field? Is that a problem?
I don't think we could find like a commercial magnetic, that amount of magnetic field. I don't think that we can find it that easily. So that's why we can use an electromagnetic current to stop it.
Okay. Yeah. That would be a bit of a problem. Maybe not a huge problem, but yes. So
Yes.
when we talk about feasibility, right? Okay. Can you go now to the actual picture of your motor that you built, please? Yeah, maybe there. Yeah. Okay. So what, Natalia, what are the pole? Which is the pole facing us from the magnet?
We use the South Pole.
The South Pole. Okay.
Yeah.
So this is the South Pole.
Yeah.
Okay. If I were to put the rod here, and I were to connect this like this, where would it move?
So
Left or right?
give me a second. It'll move right.
It would move right. Okay. Yeah, right. Okay, that's the answer. Now, so let's say that we put the rod here on this side. So it's going to experience a force in this direction. It's going to move right, down right. And your braking stage considers like an additional magnet somewhere here, right? with the opposite, facing the opposite as compared to the other magnets. How could we use the motor that you built already without any additional magnet to make the rod move and stop at the same time so it arrives here with 0 velocity? What kind of adjustment could you do to the motor for that?
To arrive with 0 velocity.
Yeah, so I would like to I would like you to suggest an adaptation to the scheme so that we have the rod moving forward, reaches some speed, and maybe halfway through the motor it starts to slow down until it gets here with zero speed. How would you change things here to achieve that?
I think, I mean, I really don't know, but I assume I could change the poles, the polarity of of some magnets, in this case, the more right ones, to north. So it's, and maybe with a less intense intensity of magnetic field. So it starts to decrease, but in little steps and not just like, I'm sorry, I don't know the word in English.
All of the sudden?
But start decreasing like little by little. So I think I will use north facing poles in the last, I don't know, 3 magnets, but with a magnetic field with less intensity than the accelerating ones.
Okay, your suggestion for flipping the magnets on this side is quite good, because then what would happen to the force?
It will change direction. So
it will switch directions, right? So it would point this way, so you would be deaccelerating the rod. But wouldn't you want the same acceleration force as the deacceleration force?
Yes, now that I'm seeing it, and now I organize my ideas. I mean, I have 8 magnets, so I will change 4 of them to the north pole, and I will maintain the same magnet. I will just flip them, 4 of them, because I have now 4 accelerating, 4 of braking with the same magnitude. So as the force will oppose each other, it starts on 0 and it finishes on 0. I will do that.
Yeah. Okay. Good. Cool suggestion. Okay. That's it. That's it for me. Thanks.
Well, thank you very much, guys. We have David on the house. David, do you want to ask anything? Something else?
No, sorry, I arrived late, so it will be improper from my part. So, well, I just congratulate everyone.
Okay. Thank you very much. Guys, you can stop your recording right now, and remember that in the same space where you saw your schedule and the points and all that, you should upload